I'm a software engineer from Facebook, and today Namit and I are going to present the join strategies in Hive. So I think most of people know what Hive is. Hive basically is a SQL compiler which will compile the SQL query to the MapReduce job and submit to the Hadoop cluster to run. There's millions of the SQL query will be run in our cluster every day, and we can see join is the most expensive operation. So here's the motivation. We try to optimize join as much as possible. Here's the basic agenda. So first we talk about how the common join works in Hive, and we'll see there are some problem for this common join. It works for most of use case, but if some of the table is small and some of the table is bucket, some of the key is skewed, there's a lot of optimization we can do for this common join. So we'll go through each of the join strategies, and I'm going to present the common join, the map join, and another colleague, Namit, will present the others. So first, we can see what is common join. So for example, if we want to join a table X with table Y, so you will launch a MapReduce job, and some of the mappers will read the data from table X and emit the join key and the join value. And the other mappers will read also from the table Y, also emit the join key and join value, and put them into the shuffle stage. The shuffle basically to sort and merge all the results and put them into a reducer. And the reducer can get all the same join key and join value and do the in-memory join. So we see this is the common case, but it's very expensive to do the shuffle stage and do the reduce stage. And in some cases, we just need to sort one of the table. If the table is very small, we can even fit them into memory to do the in-memory sort. And we can save the shuffle stage and the reduce stage. And also, if one of the table is bucketed by the join key, if this table is too large to fit into memory, and we have some bucketed key, we can just split this bigger table join to some small tables join to do the map join. Also, if these tables are already sorted, we can save the shuffle stage. And in the reduce stage, we do the in-memory join. So if the key is very skewed, and they will have the long tail problem when you do the join. So we try to solve this problem either. So first, let's talk about how the map join works. So usually when you do the map join, the user should give the hint like which table is the small table you want to fit into memory. So here's basically how it works. They launch the map reduce join task, which is only a map only task. There's no reducer yet. So each of the mapper will load the data from the small table and fit them to memory and just basically to put the join key and join value into the hash table. And the mapper also, by design, they will read each record of the big table's data and do a join one by one and output the result. So by this optimization, we can see the small table's data will be hot and it will be the performance bottleneck because thousands of the mappers will try to read the small piece of data at the same time. So one of the optimization is like we launch a MapReduce local task which will run on the locally or even just the one machine in the cluster, which will load this small table's data. And they will output the join key and join value and put into the Hadoop distributed cache, which will populate all the files to each mapper's local disk. And each mappers can just read this data, load this small table's data in the memory, and do the map join as before. So what we save here, right now the small table's data will not be the performance bottleneck because they got this from the distributed cache, and we can turn the parameter of the replication number of this distributed cache, so we can populate as much as possible. So most mappers just read data from the local disk. And as we mentioned before, users should use the hint to say which table is the small table so they can use the map join. And actually, not all the users will use this new feature. And sometimes they give the wrong hint, and sometimes they just don't give the hint. And we try to convert the common join to map join as much as possible because they will save a lot of CPU and they will increase the performance a lot. And the way we do this is we try to create a conditional task before the real join task begins. The reason is we don't know the output of we don't know the table size at compile time, because some of the table size is the result of some subquery. So we only know the table size at the runtime. So we'll create a conditional task. The conditional task is basically they look up, because when the conditional task is running, they know the table size for each table. And they will figure out which the best way to run this join. So in the compile time, they generate all the possible solutions. And in the runtime, they figure out what's the best way to do this. So here's the example. For example, we want to we want to join table X with table Y based on the same join key. So during the compile time, they generate all the possible solutions. And during the runtime, the conditional task see the table X is the bigger table, and the table Y is small enough to fit in memory. They run the map join task. So if they think both of these tables is too large for the map join, they just run the original common join task. And right now we already bound the input file of the map join, but sometimes you may select too many join values. So there's also a possibility that if you want to load all this data into memory, they still run out of memory. So we bump the memory size of the local task. We measure the heap size. If we running some high watermark, we just abort this task and run the original common join to back up. And in this way, this is totally transparent to users, so the user don't know what's going on there, and they just try the map join first. If they not work out, they try the common join. So they try the file size first. If the file size say you need to run common join, then you run common join. If not, they still try to load this file into the memory, and if it fails or anything, they just run the common join. So here we can see the distributed cache may be the potential bottleneck for this map join strategy, and we can tune in some parameters to see to improve the performance. Also, we have a lot of compression to try to save some space. So here is the bucket map join, and welcome Nemeth to talk about this.
Some of the techniques that are being used, which enables the users automatically to select the map join, which is very good. But in many cases, what we have seen in our warehouses that we have like very small number of very large tables. So like 90% of our data consists of like top 20 or 30 tables. And if we can do any special casing for those tables, we can save a lot of CPU and a lot of space. And essentially, we are like nearly 100% CPU bound. So if we can do any special case for like a small number of specific tables, and most of those pipelines are written by like slightly advanced users. So if we can provide some techniques for them, they can use them and like basically save a lot on the CPU. So one thing is in the Hive data model, like there is a table and there is a partition. I mean, essentially a table consists of many partitions. We also have the notion of buckets, where a partition can be bucketized. So like a bucketize can be as simple as like a hash distribution by user ID, etc. So here the idea is that if you are doing a join of two tables, like you don't have to join the two tables completely, but like if the number of buckets happen to be a multiple of each other, you can join the buckets, and that way, and then union all the results. So the only restriction is that the bucket columns have to be the same as join columns. Now this is a fairly common scenario, especially for big tables. So the way this can work is, for example, if you're joining like three tables, A, B, and C, and A has 2 buckets, B has 2 buckets, and C has 1 bucket. So now, I mean, essentially the join is same as saying join bucket 1 of A with bucket 1 of B and with table C, and similarly join bucket 2 of A with bucket 2 of B with bucket C. Now, this can scale. The main advantage of this approach is that each table individually may not be a candidate for a map join. For example, A may be like a very large table. B may be a very large table. But now if you split it up across a large number of buckets, then each bucket may individually fit in memory, and then it becomes a candidate for map join. So for example, a use case that we have is like Facebook contains the user data and the dimension data, like the user dimension data. For example, what is my age, what is my birthday, etc., etc. Now that dimension data does not change a lot. So what we found out was that the rate of percentage change was like 0.02% or something like that. So previously we used to scrape all the data, perform a join in Hive, and that used to be a very expensive operation. So what we did was we compute like we divided the data into like 10,000 buckets, and each bucket is reasonably small to fit in memory. And we capture the change log from the web tier, and then we do like a bucketed merge join. And since the changes are pretty big to fit in memory, but if you divide it by 10,000 buckets, each like the number, so for example, even if the change is like 10 gig, if you divide by 10,000 buckets, each bucket can easily fit in memory, and then it becomes a candidate for map join. The only thing here is that Hive does not today let the users automatically choose this because bucketing and sorting, so it's not reliable, as in like even if the user says the data is bucketed and sorted, it's not guaranteed that the data will be bucketed and sorted. So unfortunately, unlike the previous things that Liyin said, this is not automatically enabled. The user has to like manually give some hints to make sure that bucketization happens. And again, the main advantage is the mapper is run based on the big table. The small table is divided into lots of buckets, which are completely run in memory. And only matching buckets of small tables are replicated into each mapper. So we are reading the minimum data of each mapper. And in production, there will be like thousands of buckets. We also support sort merge join. So here there is no, again, in the bucketed merge join, there is still a limit on the size of the partition. Size of the bucket, because each bucket has to be read in memory. And that limit can be increased as the number of mappers increase, but there's still a limit because most of the clusters have a practical limit on the number of mappers per job, etc. So here, if the data is already sorted, then the merge join is essentially like even simpler. You just scan one, like forget the bucketing part. But if you think just about two tables, you're looping over one table and like scanning the other table, and you're doing a sequential scan of both of them. And there is no limit on the size of each bucket or each table. Again, the catch here is that Hive, although the metastore says that the data can be bucketed or sorted, it is not enforced. So Hive does not know for sure that the data is actually sorted or bucketed. So user has to manually give some hints to actually say that use sort, merge, join, etc. And the other restriction is that the bucket columns have to be same as the join columns, which have to be same as the sorted columns. This is a simple example of like where we are showing like the mapper is running on table A, and the appropriate bucket of table B and table C is being scanned as and when you get that row. And this is a simple sort merge technique that, I mean, I guess it's pretty straightforward. Like you're looping over like the records in A. When you find a record in B, you just go down, etc., etc. So here the key is that you're dividing A into various buckets, and the only restriction is that each bucket of A has to be read in by the mapper. B and C are completely sorted, and there is no requirement of the size restrictions. A common use case for this that we found was like we compute for ads like a rolling aggregates, like last 30-day aggregates, last weekly aggregates, or whatever, 6-monthly aggregate. So instead of computing all of them every time, now we are computing daily aggregates and then merging all of them. And this, again, it's only it's a complete map-only job, and this scales very well with the number of mappers. The only restriction is the number of mappers. No reducer, no shuffle involved. Another very common problem that joins typically run into is long tail. So it's very common with ads. Like there are few big ads that take like a lot of the data, and there are two main problems that happen. Basically, the last reducer or whatever, the reducer that gets the data for that skewed key gets a lot of data. So first of all, there's a lot of CPU wasted in the shuffle phase and the reduce phase. And then the reducer that actually performs the join becomes a real bottleneck. For example, if there are like 100 million rows from table 1 for one key, and even 100 rows from other table from the other key, the reducer that will emit like 10 billion rows will spend a lot of time like churning over those, like essentially doing the multiplication and doing a lot of time. So basically, we have solved the problem we have solved the second problem. We have not solved the first problem where the reducer does not get the data. But we have solved the second problem, that reducer does not have to like consume the CPU to do the multiplication. So here are some parameters, and these are turned on by default in our warehouse. And basically, you can optimize the skew join. So essentially, the way it works is that when the reducer gets the number of, the reducer keeps the threshold on the number of rows it sees per key. And basically, when the threshold exceeds a certain limit, instead of performing the join on the same reducer, it essentially defers it. So for the smaller keys, the join will be performed as though it was a normal join. For example, K2 and K3, the join is being performed. But as you can see, like that from table A, the number of rows for key K1 is way beyond the threshold. And in that case, it will write it to temporary HDFS and just leave it. And then the first MapReduce job will actually perform the join, excluding the big keys. And then a follow-up job will be launched specifically for the keys which are large. And in that case, the A's, since it's only for key K1, the B will be performed as map join. So now job 1 and job 2, basically job 1 contains the data for all the keys other than K1, and job 2 contains the data only for K1. And job 2 is not the bottleneck because it was done as a map join, and there was no shuffle needed. And then basically automatically a union of these results were performed. The only problem that we are still working on is like basically the reducer still needs to get all the data for K1 before it can actually perform this. So it's not detected at compile time because again, as Liyin said, this can be based on a subquery, and we don't have appropriate statistics to determine what is the size per key right now. This is something about like the numbers. We have like a large cluster. I think I can skip this. And these are some performance numbers. I won't go over them in detail, but essentially we have all these things have been deployed in production since last 3 or 4 months, and you can see that there is a lot of performance improvement. And again, the key here was that what we noted was like the normal user or the non-sophisticated users, they don't want to tune in many parameters. So if you give them simple parameters, if the same query works without any changes, that's good. So I'll skip the performance numbers. So I'll just go over some summary and future work. So basically, map join has been supported since Hive 0.5, but the new map join was launched in Facebook like for a few months now. It's been in production for probably 3 or 4 months. And one thing we are working on is the memory efficient hash table, because that essentially determines how much data can we hold in the memory. Other thing which we have recently launched in Hive is the sampling. So now you can do like sample 1% of the data or sample 2% of the data, etc. But we don't have sampling based joins, which is like a very well understood problem in research, and I mean that is what we should do. So that is something that we are looking at. So essentially the idea there will be that if by sampling you can figure out the hotkeys even before doing the join, then you can skip those keys and then do them like I said here. Something like this, but instead of figuring out that the skewed key at reduced time, if you can figure out the skewed key at mapper time or at compile time itself, then you can skip the key K1 at mapper time, and then this job will be really fast. So that is being worked on. The other thing that we are being worked on is the index joins. So right now, somebody recently added in open source support of indexes. So that is something we are not using currently for joins, but yeah, that is the other thing that we are being worked on. Yeah, that's pretty much it. I can take more questions.
Got a question. So have you guys looked into using like a kind of local persistent storage instead of fitting everything into the memory for joins? So like using like Berkeley DB or temporarily like storing like medium-sized tables.
Sorry, I didn't understand you.
So like one of the earlier slides showing that smaller tables will fit into memory, and then there are bigger tables when you're doing the map size join. But then like when the small table does not fit into memory, you're gonna fault it and then just actually just do the regular join. So have you guys looked into like alternative way to kind of using, if it's a kind of medium-sized table and you're kind of using local kind of persistent storage like Berkeley DB or to kind of
So the question is like, have we thought of like scenarios where the small table cannot fit in memory? So there are two ways to do that. So one is like the bucketed join that I talked about, like if you can bucketize the data and the join happens to be on the same key. And the other one was the index join that you were talking about. So we are in a very preliminary stage right now. We haven't really thought about it, but for that we need basically indexes, and we don't have the lookups right now. The Hive does not support a plan where essentially you are doing an index-based join on some other storage. So we haven't done much work on that. That is something we are thinking about, but not spent much time.
I had a question about the skew join that you mentioned. So how is it that, so you said that once you recognize that there is a really large key, and you kind of take it out of the critical path temporarily, but then you have a second job that goes and processes that. So how is it that you're saving time overall for that job with or without the join, without that optimization?
So basically, there are two main bottlenecks. The first bottleneck is the reducer itself was a bottleneck because it got so much data. So we are not saving that time. But essentially, the way it works is you are doing a multiplication if you don't do this. So for example, let's take this A and B, the key K1. If A had, say, whatever, 1 billion rows for key K1, and B had, say, 100 rows, then you are actually, if you don't do this optimization, the reducer is emitting 100 billion rows. And it's essentially doing a multiplication, going over like data again and again. So now, if we defer this, so we are writing only the K1 to a temporary storage, some storage. And B is small, so it will fit in memory. So in the follow-up job, now B will, so now think of it that you are only doing a join for key K1. And K1 can have like 1,000 mappers. So each mapper will read a very small portion of the data, whereas B will be replicated to each of them because it's small.
Okay.
So you are saving, the follow-up job will be very fast because you're parallelizing on K1.
I see. So that's in the case where you're doing some, I guess it's a join, but you have outliers in other parts of your job as well, right? So this is, I guess, very targeted towards where you're multiplying a small table to a bigger table.
Yeah, this is only for joins, but this is not limited to one key. So you can have multiple big keys. So you can have, like, typically what we have seen is like there are like few big keys. And so you will have a separate MapReduce job for each big key. And that table will be like broken up, and that will be parallelized. So I mean, job 2 is just an example. You will have job 2A, 2B, 2C, one for each key, and then a union of all of them will be performed.
Thank you.
I was wondering if you have any best practices for choosing your bucket keys to make sure they're consistent across your tables.
Sorry, come again?
Basically making sure your bucketed keys are consistent across tables to make the bucketed join work across tables.
As I said, like in our warehouse, what we have seen is like there are few big tables in the cluster, and they consume a lot of space and a lot of CPU. And typically, like those are kind of handwritten, and the joins are, I mean, they're not that dynamic. I mean, you are doing joins on some specific set of keys. So there you can spend some, I mean, and other very common thing is that those joins are performed daily or like weekly or at a very like regular interval. So yeah, we don't have, that's a very like custom kind of thing. So you look at the data and then figure out like what you want to do.
I have a question. So the bucketization strategy, is it dynamic? Do you decide the number of buckets in advance, or is it decided based on the data set?
No, the number of buckets is static, so it's a metadata property. And what you can do is like basically there is a parameter in Hive which we have set to true by default. So even if you set you have to specify the number of buckets and the bucketization key, and then the data will be automatically bucketized.
So is that bucketization a range-based or hash-based?
It's hash-based.
Okay.
But what works is if the number of buckets has to be a multiple of each other. It need not be exactly the same for the join to work.